Hello, welcome to another video of Renesas Timing University. I'm Steve, and in this video, we're going to be talking about power supply filtering. In a previous video, we talked about power supply noise. Here we're going to talk about how to mitigate it. Now, the simplest filter would be an RC filter, which is a low-pass filter. We look at the Bode plot with a minus 3 dB point at 2 over 2 pi RC. However, at higher frequencies, things change because a capacitor, when it's constructed, of course, it has its capacitance. It also has some inductance and some resistance. So at low frequency, the capacitor noise is impedance is dominant. So let's just look at the impedance for this capacitor. So it's looks like this. At high frequency, this inductor is the dominant noise. And there comes this point where the impedance of the capacitance and the inductance is a minimum point. And this is a self-resonant frequency. So for each capacitor value, it's going to be very effective close in, but at higher frequencies, the capacitance is filtering, but higher frequencies, the inductance starts creeping in and creates extra impedance. So when we look at the filter would look something like this, like a bypass, but then the inductance starts to kick in and you get something like this. So what we do is we go with a little bit more complex filter. So a standard integration range is 12K to 20 meg. And so we can look at a filter that covers this range. So we commonly use a 10 meg, which has like this 2 megahertz self-resonant frequency. Its impedance looks like this, or it's filtering. And then we use a 0.1 because that has the minimum point here. When you combine the two, you get something like this. So it's we construct what's called a pi filter, 0.1 microfarad, ferrite bead, a 10 mic, and a 0.1. So we've already added like the 10 mic, 0.1. By adding a second 0.1, we actually take this curve and we drop it even more because the impedance drops. And when we add in the ferrite bead, now all of this gets even lower. So that is at a high level what a pi filter looks like. Now, it's a generic filter, but the great use of it is the good reason to have it on your board is that if you find that there's noise on your board somewhere, you could take one of these capacitor values and actually change it to target the frequency noise. So if there's noise at a higher frequency, we can go with a 0.01 microfarad capacitor. Now, as far as placement, it's critical that these small capacitors be as close as possible to the power pin. This one can be a little bit farther out. And if possible, avoid vias, or if you have to use a via, use a really thick one. Because again, inductance degrades the ability to filter. So keeping this very close to the power pin reduces inductance. It has the minimum value. Now, we do also recommend using ceramic capacitors. And well, this is just a quick intro to kind of give you an idea of what the power filter is and why we use something like a pi filter. But we have a lot more details in app notes. And if you have questions, just reach out. We would be happy to provide some deeper trainings to kind of explain how power supply filtering works. And that's without even taking into account like the LDO and other details like that. So thank you so much for watching this video, and I encourage you to watch more of our Renesas Timing University videos.